I do realize that the angle is really bad and half the time you're looking at my nose, so I'm sorry, but I deal with what I have. Anyway, we're done with 3 already. Great. We're almost done with the final topic. Okay, not almost done, almost halfway through. We're gonna skip magnetic fields. We're gonna come back to that in the next lesson. We're gonna jump to temporary and permanent magnets. Okay, temporary and permanent magnets. So let's carry on. What are soft? So what we're gonna learn today, the roadmap is what are soft or hard magnetic materials, and what are some of their uses. It's actually a really simple section of this topic. Okay. So comparing the magnetic properties of iron and steel. Okay. It'd be best if you could do this, but I'm not sure if you learned this in primary school. Okay, maybe not lah. So if you have a magnet, you attach a iron cylinder and a steel cylinder or block to it. What you're going to see is that more paper clips, let's say use the same magnet, so the strength of the magnet is the same, okay, and the size of this is also the same, okay. You're going to see that the iron picks up more paper clips than the steel cylinder, okay. So iron is a stronger induced magnet than steel. Okay, remember induced magnet, what happens when I attach this? Remember, it aligns the magnetic dipoles, and it aligns the magnetic dipoles in such a way where it aligns it very well. The moment it is induced, meaning the moment a magnetic field is brought near to the iron, and so it becomes a much stronger magnet than steel, and it picks up a lot more paper clips than steel. Okay, so both these iron and steel, they are not magnets, they're just magnetic materials. I move a magnet to it, it becomes an induced magnet, but this becomes a stronger induced magnet than steel. Okay, this is property 1. You're going to see that what happens if you remove the magnet. If you remove the magnet, what you're going to see is that, hey, all the paper clips from the iron one will immediately drop off, right? But surprisingly enough, when you remove it from a steel rod, some of the paper clips will still remain on the steel cylinder. Okay, what does that mean? That means that the steel cylinder somehow has retained its magnetic properties. Previously it wasn't a magnet, but now it has become a magnet. Okay, although not as strong as the magnet itself lah. But it has retained some of its magnetic properties. So iron would lose its magnetism easily, but steel does not. I hope by now, having a clearer picture of what is magnetization, what are magnetic domains, what are induced magnets, so on and so forth, you can imagine what is going on here, right? Let me see if I will talk about it. So you would imagine that in this one, when you make it an induced magnet by bringing a magnet close to it, basically what it is that this is stronger because all of them align, all the magnetic domains align very quickly and very well. Okay? But then the moment you remove it, they all misalign or unalign just as quickly and just as well, back to how it was facing previously. Okay? Steel, on the other hand, maybe they don't align as well. So previously maybe they were facing certain directions. Before they were a magnet. Oh no, I'm using the wrong mode again. Anyway, so before that maybe they were facing random directions. When you put the induced magnetic field, when you make it an induced magnet, it does start to turn to face. Maybe not so well, not like iron, but there's still enough to have a magnetic effect. But you realize that when you remove it, they don't all point random directions, they just turn slightly more away from previously. Okay, so basically it retains its magnetic property, it retains its magnetism, because the domains don't turn away completely randomly back to the way it was before. It kind of keeps its new direction. Okay, and so it kind of keeps a bit of the magnetic effect. I hope this is kind of clear to you. You don't really need to explain this, but you should be able to, based on what you've learned so far. Right, so you should be able to understand what is going on in these two different materials. And we have a term for these two different materials. We say iron is a soft magnetic material and steel is a hard magnetic material. Their properties are summarized below. Okay, so soft magnetic material is easy to magnetize and demagnetize. A hard magnetic material is difficult to or hard to magnetize and demagnetize. Okay, you can think of it as easy come, easy go, right? Easy come, easy go. But things that you work hard to get, they stay longer, right? So if you are making your notes now, you're working hard at putting it into your brain, it'll be harder to go away. If you're just listening and nodding your head, easy come, also easy go. Okay, so reminder to be taking your notes now. Okay, next. So example of a soft magnetic material is like iron. Example of a hard magnetic material is steel, L-nickel, and neodymium. Okay, what are these materials? L-nickel is basically just a fancy way of saying all the different aluminium, nickel, and cobalt. Oh no, I'm using the wrong mode again. Okay, as I was saying, aluminium, nickel, and cobalt. What's the term? Alloys, right? Basically an alloy that is made of aluminium, nickel, and cobalt. Okay, remember your magnetic materials. I need complete silence. Iron, nickel, cobalt, and steel. Okay, so these are your magnetic materials. Okay, neodymium is just another special material that you know those super strong magnets that I attach to my markers and my energy cubes and everything. You know those really small like silver magnets. Yeah, those super strong tiny magnets are neodymium magnets. Okay, these materials are hard magnetic materials, meaning that they are difficult to magnetize and difficult to demagnetize as well. Okay, and some of their uses. You use soft magnetic materials to make temporary magnets, and hard magnetic materials to make permanent magnets. Okay, a bit but we'll talk about this in a while. Okay, so basically just remember that iron in general, iron is the only soft magnetic material that you learn, and iron is used to make temporary magnets. Okay, so this is what soft magnetic material is. Okay, I think that's enough. Move on. So uses of magnet, temporary magnet. What will you use a temporary magnet for? Say an electromagnet in a junkyard to pick up junk, right? When you turn on, so imagine there's a giant solenoid here. You turn on the solenoid, the current flows through. You turn on the solenoid, it becomes a magnet, a very powerful magnet. It picks up a lot of metal, and then you want to move it. This is to separate metal from non-metal. Then you want to drop it into the like the metal junk sorter, right? So imagine you turn off the current, and then all of this is still stuck to the magnet. That will be terrible, right? So you need something that will easily become a very strong magnet and also easily lose its magnetism, right? So here you will use iron. Okay, here you use iron for temporary magnets for this sort of use. Okay, so permanent magnets on the other hand, for example like a fridge, you would want the magnetic door catch of a refrigerator ensures it is airtight. Okay, I don't know if you know this. I'm sure you all do. You open fridge all the time when you sit at home, nothing to do during HBL. So the fridge has magnets at the door catch, and so it keeps it airtight. It'll be terrible if it is like iron, a soft magnetic material, and it loses its magnetism after a while, right? So you want it to be a permanent magnet, so you use steel, L-nickel, or neodymium. Okay, great. Another example of so more examples, basically like what we said earlier. Electromagnets is a application of temporary magnets. Okay, electromagnets. So electromagnets, like just now the junkyard sorter, it's also used in a circuit breaker and electric bell. So a circuit breaker. Okay, I give you electric bell first. So electric bell, basically how it works is that when you turn on the switch, okay, We turn on the switch, current will flow through. Current will flow through this solenoid. This solenoid is this solenoid is temporary magnet. Okay, so it's an iron, it's a soft magnetic material. This solenoid will become a magnet, right? This iron bar will become a magnet. This will attract this spring. It will attract it down to touch it, right? So instead of being here, it will bend down to touch it. When it bends down to touch it, what happens? The contact point here will be broken, right? So the circuit will be open. And when the circuit is open, what happens to the magnetic effect? Because it is iron, it's a temporary magnet, it will lose its magnetic effect very quickly. And so this bar will move back flat again. Does that make sense? Because it's no longer magnetic, it will no longer be attracted to it, so it will move back flat again. But it moves back flat again, the contact point will close again. And when the contact point closes, what happens? Circuit is closed, this becomes a magnet and then gets attracted down again. And then you can see that this thing will just keep moving up and down, up and down, up and down, up and down, up and down. It will just keep repeating itself. And what happens if you put right down? The striker will hit the bell, ding, 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 ding. Okay, so that's how an electric bell would work using a soft magnetic material. Pretty interesting, huh? Okay, next. Another example is using a circuit breaker. In a circuit breaker, okay, and of course separation of magnetic materials from non-magnetic materials in a script. That was the example I gave previously. Okay, hey, where's my circuit breaker picture? I think I stick the wrong picture. Okay, never mind. Idea is there, you all know can already. Okay, so circuit breaker also same thing when the electricity surge is too great. Remember, circuit breaker breaks the circuit when the current is too high, right? So how does that work? When the current is too high, it will cause the soft magnetic material, basically the iron rod, to become a very, very strong magnet, such that it will break the circuit. So the same idea as this lah. Okay, it becomes a very, very strong magnet, strong enough to pull this down and break the circuit. Okay, and of course, when you want to reset the circuit breaker, you need this to be you need the iron core to lose its magnetism in order to reset the circuit. Okay, so this electromagnet thing. Okay, permanent magnets. What do you use permanent magnets for? Magnetic door catch. Oh, okay. Apparently that's it. Of course there are a lot of other applications as well. Okay, but I think these are the a few that you can just remember. Okay, so let's go to handout 1, question 6 to 7. Okay, once again, you can pause the video and try the questions, and when you're done, you can resume the video. Which material is most suitable for use as the core of an electromagnet? Remember, electromagnet is something that you want to be able to lose its magnetism when you turn off the electricity and have a strong magnetism when you turn on electricity again. Right, so there's only one material. You want easy come, easy go. It is a temporary soft one, which is iron. Okay, so answer is C. Question 7. The diagram shows a circuit which has been closed for some time, which would be the result of opening the switch in the circuit. Okay, so you see there's a circuit here. It has been closed for some time, so it's been closed for a while already. It's a steel ball. Okay, it's a steel ball. When you turn off the circuit, when you open the circuit, what will happen? The electromagnet. So what is the electromagnet's material? Okay, electromagnetic material, you're expected to know the electromagnetic material is always iron. Okay, it's always iron. So the electromagnet is a soft magnetic material, so it will lose its magnetism. Okay, but the steel ball will still be a magnet, right? It will still be a magnet because steel is a hard magnetic material, and it will retain its magnetism even after the circuit has been switched off. So you will expect the steel ball to still be attached to the electromagnet, because the electromagnet's material is still iron, it's still magnetic material. So this becomes an induced magnet, and it keeps its magnetic properties, and so it will still be attached to the electromagnet. So the answer is B. Okay, I hope you managed to do that. Again, this is learning objective 4, and it's always helpful to look back up at what you're learning, what Cambridge wants you to learn, which is distinguish between the properties and uses of temporary magnets and permanent magnets. Iron and steel are the two main properties that you need to know, the two main materials that you need to know. Okay, so with that, we're done with temporary and permanent magnets. Told you it's pretty easy. What are soft and hard magnetic materials? Iron is soft, steel is hard. Iron means easy come, easy go. Steel means doesn't become that strong when as an induced magnet, but it retains its magnetism better than iron. And some of their uses is temporary and permanent magnets. Okay, so with that, here's some additional homework for you. Worksheet 18A, question 4. Just take a screenshot or something. Okay, so all these in red are the new questions that you need to do. All the black are questions that you're supposed to have already done. Okay, remember to keep doing your homework regularly so that it doesn't all pile up on you at one shot. Okay, it's also good recap to see if you understand what you have learned. Okay, then I'll catch you in the next lesson.